Thursday, we definitely move it to Monday. And that would mean that, we'd have Tuesday review for the final. So, we'll see how it goes this week, you know. And, I'll talk to you more about it tomorrow, Wednesday. We definitely have that test on Monday though. Hey, good evening, everyone. Hey, so today we're gonna, work in sections 5.2 and 5.3. This involves these definite integrals that we're working on. I put two things on the board. I mean, if you want to copy, you can. There's more wording from the textbook. I want to tell you what pages I got these from. This one right here, I didn't finish the whole the theorem, but this is called the Fundamental Theorem of Calculus Part 1. So I'm going to write FTC Part 1. And then this is called the Fundamental Theorem of Calculus Part 2. Okay? This was the last thing we did last class. But this gets stated in section 5.3 of the textbook. The Fundamental Theorem of Calculus Part 1, Part 2. I didn't put all the wording down though. And you can definitely see all the writing, which is on page 388 and page, what's the next page? Page 391. They include this wording. If f is continuous on the interval, closed interval a to b, then the function g is defined by this. So I want to point that out. If you want to put all that extra wording, here's the gist of it. We're saying, okay, as long as that function g is, you know, continuous on that interval a to b. Same thing with part 2. You'll see that written on page 391. They start out, if f is continuous on the closed interval a to b, and you get part 2's there.
Now, on part 1, g prime of x equals what?
Yeah, so I left it blank. And I bet you can come up with it.
F of x?
Yeah, so what do you think? If this integral, as we noticed, was finding the antiderivative, what would happen if we took the derivative of that? That should put us right back to what?
Original equation.
F of x. And I'll make sure to demonstrate that to you. So I wanted to leave that blank. I want you just to let everyone think about that. You go, yeah, what would that equal? And this is the Fundamental Theorem of Calculus Part 1. If g of x is this integral of f of t dt from a to some x, well then the derivative of g should just be f of x.
Oh.
So we go, all right, it's like almost like removing that integral. It's similar to this concept, right? You take a number like 3, you square it, you get what? 9, then you take the square root of 9, you come back to a what?
3.
3. It's very similar to that concept, and we'll do an example to better understand this. So right now you're looking at this going, I'm not making sense. Why is g prime just being this f of x? We'll do an example so you can actually see it. Okay, you can actually view it, understand a function that does that. And then this is just saying, on closed interval a to b, all we have to do is take, this is a capital letter f of b minus capital letter of f of a, where big F represents the antiderivative of lowercase f. They use that notation a lot in calculus. And the uppercase, big F, is considered the integral of lowercase f. So we'll look at an example like that as well. Okay? So I think I'll start with something like this. Now keep in mind there is some extra wording, right? If the function is what? Continuous. Because what if the function wasn't continuous? What if it had holes and things like that, right? What if it's broken? All right. That stuff doesn't apply. As long as f was a continuous function. Same thing here. So here's an example. How about this? Just this function. I just want you to think about it. And then I'll write an expression like that. Or excuse me. Then how about 2x? We'll start with f of x equal to a 2x. Do you remember how to do the integral then?
Yeah,
What would you get?
x squared.
Yes, if you did antiderivative, you'd say leave the 2 in front. X squared over
2.
2? Sound great? Cool. So we're going to do a problem like that. But, if we do all this work and then we come back and take the derivative, then we should come back and do a full circle and come back to a what? Like a 2x. Does that make sense? So let's try something like that. Keep in mind the way this is written, see this letter A in here? That's any constant. That would be any constant that's, you know, where x is between A and some value B, or B can anywhere down the line. B can be some value way down the line somewhere. You go, where's B in this expression? You know, off to the side, keep in mind, they said that when if f was continuous on the interval a to b. I just don't want to make you, you know, include all that writing because you will see that right in the textbook. So how about this? All right, I'm going to call this g of x. A can be any value, right? Okay, I'm going to get a 1. That's x. And I'm going to make f of t 2t. dt. All right? Hey, everyone, the function y equal to 2t, similar to y equal to 2x, isn't that function continuous? Straight line, right? Okay, good. It's a straight line. Well, if we did the antiderivative of 2t, what would we get again?
T squared.
2t squared over the 2,
2, yep.
right? These 2's cancel? And don't I have to put plus constant?
Not on the.
Plus C.
Good.
No, but not on the.
Very good. He says they're going to cancel out anyway.
Yeah,
Very good. So I'll put it, but that plus c will what?
cancel.
Will go away, won't it? Right?
Where does it cancel out with?
Yep. It always cancels out on the definite interval. And we got this x and we got this 1. So I'm going to go over here and put an x, and I'm going to put a 1. But you're right. He goes, you don't have to put that plus c. You're going to get a c minus c. They're going to subtract to be 0. Cool. Now, I got to substitute x in for what letter?
T.
T. Then I have to substitute 1 in for letter
T.
T. And then I'll subtract these. Okay?
Okay.
All right, let's do it. Put an x in here, you get what?
X squared plus C.
All right, so I substitute the x, check it off. Then subtraction,
1 square minus C.
substitute
Plus
1 in
one.
there.
Let's see.
Just like we expected, everyone, these c's are just going to what?
Cancel out.
Yeah, they're going to cancel. So what do we get for this expression?
X
We
square,
get g of x is equal to what?
X square minus 1.
All right. Now let's see if this is true. Okay, I'm going to write the word okay. And we get x squared minus 1. So, okay, what's g prime of x?
2x.
Did we do full circle?
Yep.
Let me just have a look. It's like, oh yeah, we get it. We get this concept, you know, this idea. 2t, it became this t squared. Put these in here. Now if we went back and took the derivative, we come back to a what? A 2t.
1 squared plus c, or minus c that we put there. Where did you get that from?
That was from substituting this one, that would be called the lower limit, into this expression for t. So really, see this x and this 1 here? If you want to, Josephine, right here next to these, you could say, because this is in terms of t, we're saying t is equal to an x, t is equal to a 1, and you could substitute both of those into the t value. And we always take the subtraction. We subtract them.
Now, for the test, for definite intervals, is it okay if we don't include the c in?
Oh, heck yeah. Please don't. Because you're telling me, yeah, if it's a definite interval, what happens every time?
They can't.
They're just going to go out anyway. Every time, right? Very good. So every time you have a definite interval, when he's talking about you got this integral symbol and there's something here and there's something there, he's saying you don't have to put plus c. Right? But if there's nothing here, we'll put plus c.
What happens when x is at the bottom?
Ah, great question. We'll talk about that. That's a great question. Make sure I answer that. I love that. I'll read and we'll talk about what to do.
Isn't what's on the bottom is the root thing?
Yeah, but you know what was neat about this problem? This lower number was what? 1? Okay? We got this constant, 1, it could be a 5, it could have been a 7. when we substitute it, we just got a number over here. But what's the derivative of any constant? What's the derivative of any constant? Zero. So that's why this will always be equal to that. But it's in terms of x. Does that make sense? So when you follow all that stuff? Cool. I'm gonna make sure to do your example. And what I'm gonna do a big wall here. So this was kind of giving us a sense of part one. Let's look at part two. All right, how about this? I want you to find this. Go from 0 to 4 of 2t dt. So there's a definite integral. All right, we don't want the plus c's, right? We're not going to do it. But what is this finding? And remember we were doing the Riemann sums? Wasn't it rectangles?
Mm-hmm.
So first of all, could you tell me about this function right here? Isn't that a straight line?
Yep.
What's the slope?
2.
So I'm going to rise 2, run 1. But how far do I got to go up to? I got to go from x equals, or these are t's. Let me put t here. I got to go from t equals 0
to 4.
all the way out to t equal to 4. So I would like it if you just take a second to draw an image with this. Draw the function. What would it do? How high would this get it? 4.
8.
1, 2, 3, 4, 5, 6, 7, 8. All right. Go right there. Let me just get this thing up here. There we go. All right. Riemann sums dealt with those area of those rectangles, correct? So when we do this, this should find the exact area of that what? That triangle. And I think when we're done, we should check it. Who remembers the area of a triangle in geometry?
Half base it into height.
Half base times height. Okay, so when we're done, we're going to check it, make sure this works out right, right? That's why I didn't want to do a curve at first, so it's something you could really check. But after that, we could do it with any function, as long as it's continuous. As long as it's continuous. All right, what's the integral antiderivative of 2t?
T squared.
Divided by 2.
Good, the 2 and the 2, and these just do what?
Cancels out 2.
All right, take those out. Now I'm going to go over here, definite integral, t equals 4, t equals 0. And if you want, everyone, if you're getting used to this up here, you might write, this is where I'm going to let t equals 4, the upper limit. This is t equal to 0, the lower limit. And I'm going to substitute these in here.
You substitute the 4 and the 0 in for t, right?
That's right. And you always do not an addition, but a what? Subtraction. So what it'll do, it'll accumulate the area to 4, and then it would subtract out how far you accumulated to. So let's just see what we get. I put 4 in there, I get what?
16.
16. I put a minus. Then we substitute the
0.
and the answer I'm getting is 16. What's the area of that triangle? Half base height.
So base is 4.
Base is 4, height is?
8.
And then what's half of base 4 times height 8?
16.
16. Isn't that cool? I'm going to change one little thing. And I'm going to answer your good question about, hey, what if, he goes, what if that x was on the bottom, right? It's going to be easy too. You'll like it. Hey, let's change one thing. Ready?
So he's asking like the x is on the lower limit.
Yeah.
Okay.
He goes, what if, and he's like, what if this was x here, and then I would put a constant up here?
Okay.
And we'll go, oh, we'll come up with something real quick. All right. What if this was just 1? How would that change?
So
Then it
4
wouldn't be
squared,
16,
12.
it would be like,
And think about it. What would it find in this image? It would accumulate the area to 4, and then you'd have to subtract out the area from 0 to what?
1.
So what would that represent? The area under this line, between this line and the x-axis, but don't I have to blank this right here?
Mm-hmm.
So when look at this, this is what this is finding. It'll find that area. That's a trapezoid now. So I didn't want you to think it's always 0. Sometimes it's a 1 there. So I'll change this to 1. Now we're subtracting out what?
1.
1 squared. So what's 16 minus 1 now?
12.
15?
No, 15. Yeah. Mhm.
So what's the area of that region right there?
So base is 3. 8 times 3 is 12. No, 8 and 3 is 24 divided by 2.
Good.
So that's 12, right?
Yep, and I think a great way to think of this, Owen, if you wanted to check this, you go, how could I check to make sure we did this right? It's the idea of what? The area of the whole triangle would be 16, and you'd have to just subtract out the area of that little blank triangle now. Because that's not part of the image. What's the area of that little blank triangle? What's 1 times 2 and then take half of that?
1.
1, so you're going, oh, 16, subtract the area in there, gives you the entire area of 15 in that image. Does that make sense? That's why we're subtracting. I want you to understand, why are we subtracting? Because you're going to